Hello, thanks for tuning in to this video preview of a new tutorial that I've prepared on interferometry for shape, texture, and surface structure analysis. It's being offered by the American Society for Precision Engineering at their annual meeting in San Diego in 2025. My name is Peter de Groot. I've been doing tutorials for ASPE for many years, and I always really enjoy them. Precision engineers are wonderful students, not only because you are engineers, you're trying to get something done, but you're precision engineers, which means you want to understand the fundamentals well enough to push the state of the art. This year we're trying something a little bit different. We're going to have a morning tutorial, which is a lecture. That's what this video overview is all about. Then the afternoon there will be a workshop with practical hands-on experience with real interferometers. Here in this video I'm going to provide a quick overview of the lecture content so that you can see if this course is for you. Let's go. Here's an outline of the morning lecture. After an overview, we'll review some of the basic optical principles that we will need in order to understand the next section, which is interferometry, how interferometers work. Then we'll look at specific tools that do form and wavefront measurements, how those function, and then move on to surface structure and texture analysis using interference microscopy. And we'll finish up with some standards and good practice guidance for how to get the best out of these tools. We'll begin with an overview of interferometry and what it's used for. A good place to start is with some history, including Newton's rings. We'll then trace the history up to the 1980s when computerized phase shifting became popular. That'll bring us up to the present day. We'll finish up the overview with the current state of the art, for example, interferometry for extreme ultraviolet photolithography components, synchrotron mirrors, gravitational wave detectors, and the like. The next step is to review some fundamentals of optics that we need in order to build interferometers. We'll recall the properties of lenses and mirrors that make up complex optical systems. Since we're talking about interferometry in this tutorial, we're going to need to review some of the concepts of physical optics. These things put together will allow us to describe the optical design of interferometers. With these ideas in place, we're ready to introduce interferometry. We'll recall some of the classic and familiar interferometer designs like this Michelson geometry. And then we'll add an imaging system that combines interferometry with imaging in order to do surface topography. To understand these instruments, we're going to have to say a few things about how these instruments are modeled. When there is an imaging system involved in interferometry, it's quite interesting and also quite complicated. And we need to understand these things at a basic level in order to get the best out of our instruments. We'll even take a moment to describe how people currently are modeling interferometry using quantum computers for modeling not only conventional interferometric measurements, but interferometric measurements that use single photons and entanglement to do new and exciting things. We're now in a position to describe how interferometers can be constructed to do precision form and wavefront measurements. Just to get a feel for how this works, we'll take a look at trying to do a visual analysis of interference fringes. We'll then have a look at how a computer can operate an interferometer and do a much more accurate job. There's a lot of work going on now in the testing of A-spheres and freeforms using interferometers, together with computer-generated holograms, but also a variety of other interesting techniques that we'll tell you about. Finally, we'll discuss some advanced technologies that are now standard for commercial products, including dynamic interferometry and the measurement of multiple surfaces all at once. The next topic is surface structure and texture analysis, and this will primarily involve interference microscopy. The dominant technique in interference microscopy today is called coherent scanting interferometry, so we'll have a look and see how that works. The fundamental idea is that we're going to use not only the interference fringe phase, but we're going to use the presence of the interference fringes, its fringe contrast or its coherence, in order to do measurements of very complex surface structures. Then we'll have a look at the practical issues of choosing what kind of interference objective, what kinds of interference objectives are there, and how to choose them based on spatial frequency range and other properties such as the numerical aperture. Some advanced techniques that are also now available on commercial instruments include analysis of thin film structures in measurements over complex film structures. With some understanding of the principles of how interferometers work, it's time to take a look at standardization and good practice. One of the most common uses for standards is for terminology. For example, lateral resolution. What does lateral resolution mean? How is it quantified? These things are set down in the standards. The standards also specify specific procedures, some of which are important for calibration verification. They're also very valuable for defining exactly how data should be analyzed so that you can compare the results. And that's it. That'll be the complete lecture. Now that you've mastered the fundamentals of interferometry, you'll be all set for part 2, the practical workshop in the afternoon. Okay, well that's it for this video preview. If it looks like it's interesting to you, I'd love to see you in San Diego. Cheers.